Alright, in this video we're going to cover the entire test review for DMA 30. You'll see some questions pop up that say show your work. Just keep in mind though that you do have an hour and 20 minutes to take this test. So the work that I show on the screen is the work that I want to see. When it comes to actually finding some maybe some tough multiplication problems, I don't have to see all that work pencil and paper. And you'll see exactly what I'm talking about as we go through this video. But let's go ahead and look at the first problem. Find the ratio of the first number to the second number and simplify. For example, 24 to 32. Set it up as a ratio. In this case, we'll use a fraction. And let's simplify this. Now, depending on how good you are with your multiplication tables, 8 goes into both of these numbers. 24 divided by 8, that is going to be 3. 32 divided by 8, that gives you 4. So that's it for that ratio simplified. Keep in mind, we'll use this in a minute too, a ratio is used to compare similar units of measurement. In this case, we don't even have any units of measurement. We just have 24 to 32. But I'll mention that again in a few minutes. A ratio compares the same units of measurement. Over here for this next problem, 2.4 to 1.5. Now I'm going to show you a little secret here that I do with decimals. Notice if we move this decimal one place to the right, as long as we do the same thing at the bottom, this ratio actually becomes 24 to 15. What's a common number or common factor that 24 and 15 have? How about 3? We can divide both of these by 3. 24 divided by 3 gives you 8. 15 divided by 3 gives you 5. Now, you didn't have to show that step there. You could just, in this case, remember, you have an hour and 20 minutes on the test. You could just divide these two and convert it to a fraction. The main thing I'm looking for is the fact that you are setting it up as a ratio and you do simplify it, but you don't have to show that step right there. So 2.4 to 1.5 is the same thing as 8 to 5. Alright, problem number 2. Solve each proportion. This proportion right here, the way I showed you in class, this is one of the only times that you can cross multiply. When you have one fraction equal to one fraction, you can multiply. Now, you don't have to show me all this work. For example, right here though, 7.2 times x is 7.2x. Set this equal to the other cross product. This is the only time you can cross multiply, when you have one fraction equal to one fraction. Now here, please don't spend too much time trying to multiply this. I'm grabbing a calculator right now. 15.84 times 3.5, that's 55.44. So from here we want to solve for x, so we divide both sides by 7.2. Now some of you may skip this step. I'm okay with that for right now. We haven't talked too much about solving equations, but we have talked about this process in class quite often of multiplying and dividing should you need to divide. In this case we need to, so 55.44 divided by 7.2, we get 7.7. And I tell you what though, since I am making a video, it's a good time to check your work at least. You have a calculator, you can check your work real quick. So I'm going to plug up the document camera and we're going to have a look and make sure that these two fractions are equal to each other. Give me a second. Alright, so what we're going to do is this loads up down here. We're going to take this 7.7 and plug it in back up here and make sure we get the same fraction or the same decimal when we divide this. Let's plug 7.7 in right there since x is 7.7. So take 7.7 over here on the calculator. Let's divide it by 15.84 and we get that weird looking decimal. Alright, so 0.486 and some repeated ones. Let's see if we get the same exact decimal here when we do 3.5 divided by 7.2. .486 with some repeated ones, and if we look back at that other one, .486 with some repeated ones. So we do have the exact same fraction on both sides. That proportion does work, and it's supposed to. We're solving for x. So let's do something very similar over here. Let's cross multiply. 15 times 480. Don't waste time trying to do that pencil and paper. I don't think we quite have enough time to do all that on the module exam. But cross multiplying here, we do get 7,200. This is equal to your other cross product. X times 36 is 36x. And let's divide both sides by 36 to get x by itself. And when you do that, you get 200. So 200 is equal to x. But since I'm recording the video, let's go ahead and check this and make sure that it works. 15 divided by x. In this case, x is equal to 200. Let's see what that is. 15 divided by 200, that gives us 0.075. That is 75 1/100th thousandth. That's 75 thousandths. Let's see if we get the same thing over here. 36 divided by 480. Check that out. 75 thousandths. So we did solve it correctly here. On to question number 3. Write each rate as a unit rate. Now, earlier in the video, I talked about ratio. Ratio compares the same units. Now, in this case, it was 24 and 32. We could say 24 oranges to 32 oranges, or 24 feet to 32 feet, or 24 inches to 32 inches, 24 pounds to 32 pounds. Those are ratios. They compare the same unit of measurement. But now notice this word rate. Rate compares two different units of measurement. For example, right here, 60 revolutions in 5 minutes. So let's set that up as a unit rate. Now I'll talk about unit rate right here in a second. We got 60 revolutions in 5 minutes. Now this right here should be mental math. 60 over 5, that's equal to 12. 60 divided by 5 is 12, but make sure you include your units. What we have here is revolutions per minute. I've wrote it like that in class several times. 12 revolutions per minute. Let's think about this. If we can talk about a wheel. A wheel, this big wheel, I don't know, like a water wheel or something like that. It does 60 revolutions in 5 minutes. If it does 60 revolutions in 5 minutes, the unit rate, we want to figure out how many revolutions it does in 1 minute. 1 minute. Well, if it does 60 revolutions in 5 minutes, it does 12 revolutions for every 1 minute. And that's our unit rate right there. So make sure you include your units, which I did right here. Same thing applies to this next problem. 245 presents, I'll do that PRE, for 35 children. So we'll divide by 35 children. We can abbreviate it like that, that's fine. In that case, let's go ahead and divide that. 245 divided by 35, we get 7 presents per child. If you have 245 presents distributed amongst 35 children, if everybody got the same number of presents, there would be 7 presents per child. And all we did there was divide. So notice these two rates, since we're using two different units of measurement. We have presents over children. So a rate can compare two different units of measurement. Keep that in mind because we're going to use that again in a problem in a few minutes. Number 4, convert the following. So I have all these tables over here to the side, charts, tables, whatever you want to call them, and we're going to convert, in this case, 2 yards to inches. Don't stress about trying to memorize these. I will supply the charts, these charts right here, for you on the module exam. I just want to make sure you know how to use them. So for question A, we're trying to convert 2 yards to inches. So we're talking about lengths, and in this case we're talking about US units of length. We measure lengths in inches, yards, miles, feet, stuff like that. So we're going from yards to inches. Notice this right here. 36 inches is 1 yard. I'm going to go ahead and write that. 36 inches is 1 yard. This is equal to, now, what do we want to do? We want to convert 2 yards to inches. Now, since I wrote yards at the bottom, let's make sure we put the 2 yards at the bottom here, but we're trying to figure out how many inches, so therefore we'll put X inches. Now, if you leave these words off, I'm not going to stress too much about it. I'm just putting them here to remind you, if you're going to put inches at the top and yards at the bottom, you better put inches at the top and yards at the bottom on the other one. So when we cross multiply here, 36 times 2, that gives you 72. And 1 times x, that gives you x. So 72 is equal to x, but I do want you to go ahead and make sure you write this as 72 inches. Therefore, we can say that 2 yards is equal to 72 inches. That's what we got right here. All right. Question B. I'll just scatter these all over the place since just trying to make some room. 4,200 pounds, 4,200 pounds, and we want to convert this to tons. This is U.S. units of weight. Notice right here, we have something that converts between pounds and tons. 2,000 pounds is 1 ton. I'm going to write that out as a rate. 2,000 pounds, and actually we should be writing this as LBS over 1 ton. Set this equal to, now we have 4,200 pounds and we want to convert that to tons. So since we have pounds on top, let's make sure we put the pounds on top here. So 4,200 pounds over X tons, because notice here we're trying to convert this to tons. So let's cross multiply to solve this. 2,000 times X is 2,000X. And then cross multiplying here, 1 times 4,200 is 4,200. And let's divide by 2,000. So therefore, when you take 4,200 divided by 2,000, you end up with X equal to 2.1. So therefore, we can say, let's look back at our problem. If X is 2.1, we can say 4,200 pounds or 4,200 pounds is the same thing as 2.1 tons. So let's say 2.1 tons. And you can notice right here too, when we set up our proportion, the 2.1 was right there in that spot. Since we got X equals 2.1, therefore we have 2.1 tons. All right, question C. 3.8 meters to centimeters. Now I did give you a shortcut in class. Now we're in the metric system. I don't have just a straight up metric system. These I have here convert between metric and US. These two right here, and over here we've already used these. When we're in the metric system, we're trying to convert 3.8 meters to centimeters. The acronym I gave you was King Henry drinks Ucky dark chocolate milk. I've talked about this in class. Look back at your notes. You should know what each one of these stand for. Our little conversion here, we're trying to go from 3.8 meters to centimeters. So the way you saw it in class was 3.8 meters is equal to blank centimeters. So since we're at meters, meters represents the unit. That's a unit. That's what that U stands for. Look back at your notes for that. And we're trying to convert to centimeters. So therefore, if we look at our little acronym thing we drew out up here, we're converting meters to centimeters. So we move the decimal 2 places to the right. So if we have 3.8, you move the decimal 2 places to the right. The same thing I did up here. Therefore, we got to add a 0 so we can say that 3.8 meters is equal to 380 centimeters. Notice when you move that decimal 2 places to the right, you have to add a 0. That's how I get that 380 centimeters. We did talk about the metric system in much more detail in class. We talked about the fact that centimeters are much smaller measurements versus a meter. So if you have 3.8 meters, it's going to take a lot of centimeters, 380 centimeters, to get 3.8 meters. because we're going from a longer measurement to a much shorter measurement. So it's going to take more of these to equal that. And that's what we talked about in class, but this was a shortcut for that problem. Question D. All right, question D, we're trying to convert 7,500 milligrams to grams. This is going to be another King-Henry problem because we're staying in the metric system. We want to go from milligrams to grams. So question D, we're going to do the King-Henry again. King-Henry drinks Ucky dark chocolate milk. And we want to convert 7,500 milligrams to some number of grams. So again, using King-Henry, we're converting milligrams, which is right here, and we want to convert that to grams. Grams is going to be the unit. Recall from class lectures, the unit could be grams, liters, or meters. In this case, we're talking about mass or weight. So that's what we want to convert to, just a plain old gram. And we got to move our decimal 1, 2, 3 places to the left. So therefore, when we move this decimal 3 places to the left, 1, 2, 3, we get 7.5 grams. So therefore, we can say 7,500 milligrams is the same thing as 7.5 grams. And the thing is, a milligram has very little mass. It's very, very, very light. You probably couldn't even, if something weighed 7,500 milligrams, I mean, you could barely tell it was in the palm of your hand. Very light. But it takes a lot of milligrams to get 1 gram. It actually takes 1,000 milligrams to equal 1 gram. But the King-Henry shortcut, just moving the decimal, will help us get this answer much quicker. All right, now we have these 2 tables copied over and these 2 problems. I'm going to a new page for a couple of reasons. One, we're going from a metric system, which is grams in this case, and we're converting to a US system, which is ounces. We have these 2 tables over here, but I also went to Google and I Googled this. I Googled how to convert from grams to ounces and from ounces to grams. There's a reason why I did this. This question E right here, let's have a look at it. Let's use this table here. If we want to go from grams to ounces, we actually have 2 options. We have this one here and this one here. Now we're going to work both of these out. On the test, I'm going to give you just one of these. You might say, well, which one are you going to give me? It doesn't matter. I'm going to give you the one that I want you to use. Either one of these are correct, but the rounding can throw your answer off, and I will explain that as we work this problem out. That's why I pulled this up right here, and we'll look at this in a second. But now, let's suppose that we did have these 2 here, and you might be wondering, which one do I use? You're going to get 2 different answers. That's why I pulled this up down here, and we'll look at that in a second. So let's use the first one. The reason why we can use this is because we have grams and ounces, and that's exactly what we are dealing with up here. So let's use this rate here. 1 gram is the same thing as 0.04 ounces, based on what we see right here in this table. So therefore, since we have grams at the top, let's put 22,680 grams at the top, and we're trying to convert this to ounces, so we're going to put an X down there. If we cross multiply here, 1 times X is X, and if you multiply 22,680 times 0.04, going to the calculator for that, we end up with an answer of 907.2. So therefore our answer is going to be 907.2 ounces. According to this one that we used here, 22,680 grams is the same thing as 907.2 ounces. Now watch what happens when we use this one down here. So let's set up the same problem, but instead of us using this rate that we got here, let's use this one. So we have 28.35 grams is the same thing as 1 ounce. Setting this up, let's make sure we put grams at the top. So we have 22,680 grams, and we're trying to convert that to ounces. So it's kind of got the same setup, except our rate here is different than our rate here. So let's cross multiply. 28.35 times x is 28.35x is equal to 1 times 22,680 is 22,680. So therefore for this problem we need to divide by 28.35. And when we do that, we get x is equal to, because the 28.35's cancel, so 22,680 divided by 28.35, we get 800. It's not a problem, but then again it might be. I mean, you might be thinking, well, we're getting two totally different answers. Okay, well, x is 800. Actually, I shouldn't be boxing that. It should be 800 ounces. Two totally different numbers. And they're a long ways apart, to be quite honest with you. Now, there's nothing wrong with these two things right here, but notice 1 gram equal to 0.04 ounces. 1 gram down here is equal to 0.035274. And that is 0.04 if you round to the nearest hundredth. This is a good time to talk about rounding. Look how bad, or not bad, but look how off these two numbers are if we round too early, so to speak. Notice down here, 1 ounce is the same thing as 28.3495 grams. Well, we got 28.35 grams, but notice it's actually 28.3495, and these two numbers right here are rounded as well. But if we use these, I guarantee you we'll get an even closer answer. I don't know why that x equals is written down there, but nonetheless, let's set up this same problem, these same two problems here, but let's use these measurements and let's see if we can get a closer answer, because these two are supposed to be the same. We're converting 22,680 grams, we're trying to convert it to ounces. Here we got 907.2 ounces, down here we got 800 ounces. Let's use these and see if these two numbers here get closer together. Now, you might not really care about this, but it's worth talking about. Rounding can really throw your answers off. And as you can see, our answers are way different. So instead of us using these two, let's use these two. I'm going to use this top one first right here. So we got 1 gram is the same thing as 0.035274 ounces. Now that right there is very similar to what we have here, except we rounded to the nearest hundredth. Notice if you round this to the nearest hundredth, that 5 tells that 3 to go up to a 4, which is what we have there. We're going to set this up, and now we have 22,680 grams over x ounces. Let's cross multiply here and see what we get. So when we do this, 1 gram or 1 times x is just x. And now let's pull out the calculator and multiply these two ridiculous numbers together. 22,680 times that number there, 0.035274. Oh, look at this answer that we get. We get 800.01432. Wow. Notice, folks, we did 1 gram over 0.04 ounces and we got 907.2. Down here we did 1 gram over 0.035274 ounces. Very similar, except we rounded too early, but we got it off the table. But look how much that answer changed. Instead of it being 907.2, we now have 800.01432 ounces. Look how much closer that is to this number. So let's use this one down right here, and let's see if we get something close to 800. This number right here looks kind of crazy, to be quite honest with you. But hey, we're pulling it off the table. There's nothing wrong with that. It's just that this number was rounded, I would say, a little bit too early. We're using something like that there in that problem we just did. But let's set this one up. How about 1 ounce is the same thing as 28.35 0.3495 grams. That's what we have right there. So we're setting that equal to, well, we're trying to solve this problem still again. We're trying to convert to ounces. Notice I put ounces at the top. It does not matter. As long as I got the ounces at the top and the grams at the bottom, this is still going to work out. So X ounces over 22,680 grams. Let's cross multiply, and let me make the screen bigger. So cross multiplying these, 1 times that is 22,680 is equal to 28.3495 times X is 28.3495X. And now let's divide both sides by 28.3495. Therefore, type in this into the calculator because we are getting X by itself. 22,680 divided by 28.3495. Oh, if you type that into the calculator, you get 800.01411096. Look at these numbers we're getting a lot. I mean, for like the last 5 or 10 minutes, 5 minutes I guess, we're getting around 800. We're looking at ounces. That's the actual measurement we want to be using here. Now, what's my point in all of this? That number there is not wrong. It's just that, in my honest opinion, that 0.04 ounces was rounded. It's rounded a little bit too close. The 28.35 is rounded kind of close too, to be quite honest with you. I mean, look at what we have here. But, like I said, I won't give you both of these on the test because some of y'all might try to do both of these problems and you might freak out because you're getting two completely different answers. But in actuality, it's all about the rounding. So I will give you the one that I want you to use. Both of these will give you the same answer, but then again, you're thinking, no, they won't. It's all about the rounding. That's what you got to think about here. You might say, well, why are they so different? Well, here's what you got to think about too. Grams and ounces. Maybe you're not familiar with a gram, but an ounce is pretty daggone light. I mean, it takes 16 ounces to equal a pound. So that's why these numbers are so far off, but yet they're still kind of close. That's still a big difference, though. I'm not going to lie to you. But as you can see here, if we use something that's rounded much further down, I mean, this is rounded to the 10th, 100th, 1000th, 10,000th, 100,000th, millionth. That number there is rounded to the millionth place versus this here being rounded to the 100th place. So and we're getting numbers close to 800. These are the numbers we're looking for right here. So I got on a little tangent right there, but it was worth talking about because these two answers are so different. Again, I'll give you the one that I want you to use on the test. So maybe I confused you, maybe I didn't, but I wanted to explain that. Rounding definitely does affect your answer. So let's go ahead and copy over some more information now. Let's copy that. And now, okay, we're going to the capacity. So we're going to copy this table right here. And let's take those two pieces of information and let's go to a new page. Now this one's not going to be as bad. We can do this one pretty quick because we only have one thing over here to help us out. We're going from milliliters to fluid ounces. Bam. Milliliters to fluid ounces. That's the only one we have on this table to help us. So that's the one we're going to use. So from here, what we want to do, let's set up this rate here. 29.57 milliliters is the same thing as 1 fluid ounce. And again, this is a rough estimate. I hope you understand rough estimate. They are rounding here. This is equal to, let's make sure we set this up. We're trying to convert 354.84 milliliters. Well, let's put that at the top since we have milliliters at the top over here. So 354.84 milliliters over X ounces. And let's solve this proportion. So cross multiplying, 29.57 times X is 29.57X is equal to 1 times this number here is that number there. 354.84. And now let's divide by 29.57 on both sides. Therefore, we get x equals, dividing this, going to the calculator, 354.84 divided by 29.57. Oh, nice number. We get x equals 12. So therefore, our answer will be 12 what? We're trying to find ounces, and actually I left off something that should be fluid ounces. We are talking about a liquid here, fluid ounces. So again, there we don't have to go on this crazy tangent like I did on the last problem. I know I kind of went overboard probably with all of this material here, but it was worth talking about the rounding. I mean, the rounding really can affect your answer. And you'll hear that later on in future math classes. The rounding does affect your answer. But here, that was the only one we had on our table, so we definitely wanted to use that rate to help us find this. Alright, so on to question number 5. If 1 inch to 144 feet, oh, that looks like a rate to me. 1 inch to 144 feet. This is the scale used to build a model of the Titanic. So if this is the scale, what is the length of the model if the ship was 882 feet long? Let's make sure we put that 882 feet down here. This represents the actual size. The actual size of the ship was 882 feet. The model that we're making is like a model you can put on a bookcase or something like that. We want to figure out how many inches it was. So let's cross multiply. And again, we put the feet at the bottom, we put the inches at the top. Cross multiplying, 1 times 882 is 882. And x times 144 is 144x. Divide both sides by 144. So 882 divided by 144, we get 6.125 is equal to x. Since we're dealing with a real world problem now, we do have like a real world situation here. Let's type an answer out. We can say the model is 6.125 inches. And again, like I said, the model is something you can put on your bookshelf. It's like one of those model cars you make, except in this case it's a ship, the Titanic. But the ship was actually 882 feet long. The model that we would put on our bookcase would be 6.125 inches, based on that scale that was given to us. On to question number 6. 2 friends were shopping at different grocery stores. Lucy bought a 2-pound can of coffee for $3.38, and Sally bought a 5-pound can of coffee for $8.50. Should this situation be represented? And that word right there, we should have be represented. So, should this situation be represented by a ratio or a rate? Okay, I mentioned it earlier, way back earlier. Back at the very beginning, I think I circled something. Ratios, they compare units of the same measurement. Whereas things like a rate, they compare 2 completely different units of measurement. Notice here, this rate, revolutions in minutes, 2 different types of things. So what should we do for this problem? Now, let me make sure I get back to my problem. Here. This should be a rate, and the reason why it should be a rate, because we're talking about pounds and we're talking about dollars. They're two completely different units of measurement. So it's definitely a rate. Question A would be a rate, and the reason why we are, I'll tell you what, I want to type. It should be used as a rate, and the reason why we are comparing 2 different units of measurement. In this case here, we're comparing pounds to dollars. So Are the two friends spending equivalent amounts per pound of coffee? When you're talking about trying to compare, is one cheaper than the other and stuff like that, for question B, we're talking about the unit. What's the unit price? Well, let's look at Lucy. Lucy paid $3.38 for 2 pounds, whereas Sally, she paid $8.50 for 5 pounds. Now notice I put my costs at the top, my pounds at the bottom, because our answer, once we divide this, we're going to figure out the price per pound. Let's go ahead and do that right now. Go to the calculator and do $3.38 and divide it by 2. That's that little fraction right there, that rate. Therefore, what we have actually is $1.69 per pound. If she paid $3.38 for 2 pounds, the unit price would be $1.69 per pound. Let's figure out what Sally's unit price is. Let's divide these two numbers. $8.50 divided by 5 pounds. Sally is spending $1.70 per pound. Now, I'm not going to lie to you. I was thinking most of the time, if you buy stuff in bulk, the more you buy something, the cheaper you pay. But this is one of those situations where that's not the case. Sally went to a more expensive grocery store. I was definitely thinking, before I even did the division, I was thinking that Sally was going to end up spending less money per pound, but actually she spends just a little bit more. That's not fair, though. Sally went to a more expensive grocery store than Lucy did. Lucy got the same, actually a cheaper unit price by a penny, a little bit cheaper, but she bought less. So in all honesty, I mean, they're pretty much the same, but are the two friends spending equivalent amounts per pound? I would say no. Lucy is spending let's do this, 1 cent less per pound. Now I'm going to do that little cent symbol. See with a line through it. Less per pound than Sally. They're pretty much the same, but like I was saying here again, if you're buying more of something, typically you want to think you're paying less per pound. And most of the times in real life situations that is the case. But hey, like I said, Sally went to an expensive grocery store. She probably went to Harris Teeter, and Lucy probably went to Food Line or Walmart. Who knows? But that's how that one works out. Now, had you said here, honestly, if you said they were spending the same amount, I couldn't argue with that, because who really cares about a penny when it comes to that? A penny's pretty much worthless nowadays, it seems like. But nonetheless, Lucy is spending a little bit less than what Sally is. 1 penny per pound. On to number 7. So, question A, 7A, demonstrate 62.5% in the grid provided. Well, how many squares do we got? Looks like 100. How can we say that so fast? Well, if we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that's 10 columns. We have 10 columns because I counted 10 across. And how many rows do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We got 10 rows as well. 62.5%. Percents are based on something out of 100. So a quick way to do this would be to shade 62.5 squares. Let's do that real quick. I just shaded 10 of them. I just shaded 20 of them, 30 of them, 40 of them, 50 of them. There's 60 of them, and there's 61, there's 62, and I'm going to go half right there. So, yeah, I am being picky. I wasn't at first, but now I'm going to go ahead and fill in everything else, make it look nice, or somewhat nice. Notice what I'm trying to do here quickly is shade 62.5 squares. that represents 62.5%, because anytime you talk about percent, you're talking about out of 100. There are 100 squares, so if we shade 62.5 squares, that's going to be 62.5%. Let's write the reduced fraction that is equivalent to 62.5%. Well, 62.5% is the same thing as 62.5 out of, well, how many squares did we shade? We shaded 62.5 out of 100 squares. So when you're trying to simplify 62.5 out of 100, I want to go on a little tangent here. You could do 62.5 divided by 100. You get a decimal, but we can convert that decimal to a fraction. We talked about that. Second PRB, and we get 5/8. Where does that really come from? That is our answer here. That is a reduced fraction. We get 5/8. But hey, let's think back to DMA 20. 62.5 out of 100. Really, where does 5/8 come from? Well, really what we have here is if we take a little shortcut. And it's a shortcut if you didn't have a calculator. Move this decimal over one place to the right, so you have 625. But now you have to move this decimal down here one place over, which means we want to add a 0. So what we're looking at is 625 out of 1,000. Now, depending on your multiplication and division skills, you might not know what's the biggest number that goes into 625 and goes into 1,000. What's the biggest factor they have in common? I know that 25 goes into both of them. So let's simplify this fraction. Let's see what happens. 625 divided by 25, that gives you 25. Maybe you didn't know that 25 times 25 is 625, but it is. Let's do the same thing at the bottom. If you take 1,000 and divide it by 25, you end up with 40. So now we have a much nicer looking fraction versus that. But the thing is, we can go even further. What's something that goes into 25 and 40? How about we divide by 5? 25 divided by 5 is 5. 40 divided by 5 is 8. Bam. It is 5/8. 62.5 out of 100 is the same thing as 625 out of 1,000. That little shortcut of moving our decimal over. And then from there we have to simplify it, dividing the top and bottom by the same number. But just showing you that you do get 5/8 right there. Alright, now looking at number 8, 9, and 10. Numbers 8, 9, and 10 real world problems, so let's make sure we leave our answers in complete sentences. Number 8, one year a pumpkin patch sold 1,200 pumpkins. The next year they sold 900 pumpkins. What was the percent of decrease in the number of pumpkins sold? The percent of increase and percent of decrease is all about whether you go up or down in regards to sales, in this case selling pumpkins. So the formula I gave you in class was, I told you this, I said find the difference between the two numbers. And then what you want to do, this is where you have to be extra careful. You want to divide that difference by the old. You have to do it by the old. Old meaning the one that occurred first, so to speak. So let's do that in this problem, but we have some more work to do after that. The difference between the two numbers. What two numbers are we talking about? One year they sold 1,200. The next year they sold 900. So that's our difference. The difference means we want to subtract. Now be careful here, the old. Which one is the old number? One year they sold 1,200 pumpkins. The next year they sold 900 pumpkins. So the old is 1,200 because it says the next year. That's the newer one. This is the old one. So we got to make sure we divide by the right number here. In this case, we're going to divide by 1,200. That was the older number, so to speak. So if we subtract 900 from 1,200, that gives us 300 divided by 1,200. And if you divide this, you actually end up with 1/4. Or you might end up with 0.25. Go ahead and use your calculator there. Make sure, double check. 300 divided by 1200. You get 0.25. What was the percent of decrease? Now here's where you got to make sense with this problem. This was the old, this was the new. Notice they did decrease in sales. The older year they sold 1200. The year after that they sold less. So they actually dropped in the number of pumpkins they sold. Now let's convert this to a percent. We move our decimal 2 places to the right. So therefore we have 25% decrease. So now let's leave our answer in a complete sentence. Therefore we can say there was a 25% decrease in sales between these 2 years. Now I know I mentioned in class 2 about signs. It is a negative 25%, but since I'm using the word decrease, that represents the negative. So there was negative 25%, but it makes more sense to say there was a 25% decrease in sales between those 2 years. And that is the percent of decrease for that problem. Be careful again about the top part's not bad. You can get away with not getting those two numbers in the right order. It's that old number that you want to make sure you get right. That does change everything. So number 9. The cost to repair a car after a collision was $4,000. The automobile insurance company paid the entire bill except for a $200 deductible which the driver paid. You get in a wreck, you got car insurance, you got to pay a deductible. Most of us do. There are some insurance policies where there's zero deductible, but good luck paying that premium every month. So nonetheless, you get in a wreck, you have a car wreck, you got to pay a deductible. In this case, the driver pays $200, but the cost to repair is $4,000. I mean, I'd be more than happy to pay $200 if it costs $4,000 to repair my car. That's why we have car insurance. But the question is, what percent of the cost did the driver pay? Well, there's an easy way to approach this problem. We can take the price that we paid, divide it by the cost or the cost to repair the car and all. Take the cost that we paid divided by the cost to repair the car. Divide those two numbers. 200 divided by 4,000. Therefore, we get 0.05. Now, it says what percent. Remember to move your decimal 2 places to the right. Therefore, we paid 5%, or the driver, not we, but so therefore we can say the driver paid 5% of the cost. That sentence is fine. Now, that's the quick approach. Maybe you don't quite understand why we divided the 200 or 200 divided by 4,000. But what you can do is this. You can ask yourself this question, or you can do the is over of equals percent over 100. But what I like to ask myself is this. 200 out of 4,000 is equal to what percent out of 100? 200. You paid 200 out of $4,000. What percent of that is out of 100? And remember, percent is out of 100. So if you cross multiply here, this causes a little bit more work though. 200 times 100, you get 20,000. And this is equal to 4,000x because that's the other cross product. And if you divide by 4,000 on both sides, you get 5 is equal to x. Now here's the difference you have to, or the slight difference in the problem. We get 5. We said the answer was 5%. Here we don't have to move our decimal because since we're already talking about it being out of 100, this number will represent our percent. 5 out of 100 is 5%. I like the shortcut, y'all. I don't know about you. Just take the price you paid out of how much it cost and all. You're going to find what percent that you paid of that car repair, so to speak. And I keep saying you and we, but this is some driver. But maybe we've been in this position before. Maybe you've had a car wreck. You had to pay a deductible. In this case, if you got in a car wreck, it costs $4 grand to fix the car, but you only paid $200. You only paid 5% of that total cost. Thank you, car insurance, I guess. Anyway, on to number 10. One car went 1,235 miles on 51.3 gallons of gasoline. Right there, I like those numbers. I'm thinking miles per gallon. 1,235 miles on 51.3 gallons of gas. Another car went 1,456 miles on 55.78 gallons of gas. Which car got better gas mileage? And that's exactly what you would probably ask yourself in this situation. If you drove 1,235 miles on 51.3 gallons of gas and your friend drove 1,456 miles on 55.78 gallons of gas, which one of y'all got better gas mileage? Now it says show your work. That's the work I want to see. I don't want to see all this division. You don't have to do long division and show all that work. Go ahead and go to the calculator and type in 1,235 divided by 51.3. What you're actually finding is the unit rate. In this case, if we take 1,235 divided by 51.3, let's round this to the nearest tenth. So we end up getting 24.1. Now how about I write it like this? MPG. If you drive 1,235 miles, that's a long ways, but you're using a lot of gas, 51.3 gallons of gas, you're averaging out 24.1 miles per gallon there. Let's do the same thing over here. Go to the calculator. 1,456 divided by 55.78. Oh, look at this one. 26.1 miles per gallon. Which car got better gas mileage? This one did. You want the higher number. You want a higher MPG. You see these commercials on TV all the time. 40 miles per gallon or 50 miles per gallon. Ridiculous gas mileage. The higher the MPG, the better gas mileage you're getting. So, therefore, we can say the car that went 1,456 miles on 55.78 gallons got the better gas mileage. And the reason why, your work's right there. This car got 26.1 miles per gallon, whereas the other car got 24.1 miles per gallon. But they're both still pretty good gas mileages. It depends on what you're driving. If it was a car, not so good. If it was a truck, I'd probably be pretty happy getting that gas mileage. But nonetheless, on to number 11 and 12. Phil decided he needed to lose a few pounds. He saw an advertisement for an exercise program that claimed a person could safely lose, I see a rate. A person could lose 3.5 pounds every 3 weeks. I'm going to write that over here. 3.5 pounds every 3 weeks. If he wants to lose 14 pounds, how many days would it take Phil to do that on the exercise program? Be careful. Be careful. Look at what you got right here. How many days? All right. The rate that we have here is 3.5 pounds per 3 weeks. Let's be careful here. We want to figure out how many days. We don't want to figure out how many weeks. This is in weeks. Now I'm going to leave it up to you to realize this, but 3.5 pounds in 3 weeks is the same thing as losing 3.5 pounds in 21 days. You got to be careful there. You got to read these problems. We didn't say we lose 3.5 pounds every 3 days. We said we lose 3.5 pounds every 3 weeks. That's the same thing as losing 3.5 pounds in 21 days because there's 7 days per week, so 7 times 3 gives you 21 days. This is the rate that you want to use. Now we can solve our problem. If he wants to lose 14 pounds, notice I'm putting pounds at the top. We want to figure out how many days. Notice days are at the bottom now. We didn't have weeks. We had it back here, but not now. Now we can solve this problem. So take 3.5 times x. Therefore, you have 3.5x. This is equal to, take 14 times 21. We're cross multiplying. 21 times 14 or 14 times 21. However you do that, you will get 294. And let's divide by 3.5 to get x by itself. Therefore, we have 294 divided by 3.5. That's equal to 84. It's not 84 weeks, it is 84 days. So don't forget your complete sentence. It would take Phil 84 days to lose. How many pounds do you want to lose? What do we say? 14 pounds. Now you might say, okay, what about weeks? Who cares? It doesn't matter about weeks. It said days. Now, if it takes 84 days, you could take 84 divided by 7. It would take Phil 12 weeks to lose 14 pounds. But since we want days, we're going to leave it in 84 days. Question number 12. Shoes Galore is obviously a shoe store with a big sale sign in the window that says buy and save. You want to buy 2 pairs of shoes or 2 pair of shoes. One pair of shoes costs 50 bucks. So that's kind of important. I mean, that's the first pair of shoes, 50 bucks. The other pair costs $32. One offer says buy 1 pair of shoes, get the second pair of equal or lesser value half off. And the other offer says buy 2 pairs of shoes, 40% off each pair. Decide which offer is best for you. Let's show you work. Now, I don't want to see all the calculation. I just want to see some basic setup. So let's look at the first offer. Buy 1 pair, get the second pair of equal or lesser value half off. That is very common. I see that kind of sale going on in stores everywhere, especially shoe stores. So you buy 1 pair of shoes and you get the second pair of equal or lesser value. That means if you have these 2 pairs of shoes, you got to buy this pair here at full price according to this offer right here in blue. But what happens though, we buy this pair for 50 bucks, we get this one for 50% off. So actually what happens here with this first offer, what we end up doing is we end up paying $50 plus 50% off that. Really what 50% off means, or half off, means you're going to pay 16 bucks for that pair of shoes. Because half of 32, half off, half of 32 is 16. Therefore, the total price there will be $66 before tax. Now, you might say, well, why did I have to pay 50 bucks for this one and get half off on that one? Why couldn't you pay 32 and then pay half off on that? The reason why is because buy 1 pair, get the second pair of equal or lesser value. That means you have to pay full price for the more expensive pair. Equal or lesser value, this is a lesser value, so you get half off of that. That's where that 16 came from. And that's all the work I want to see for the first deal, or the first offer, so to speak. So there's our first offer. We're going to pay 66 bucks. Now for the second offer, there's a little bit more math to do. We buy 2 pairs of shoes and we get 40% off each pair. Here's how I'm going to do this one though. A quick way to do this without solving a proportion is you want 40%. You get 40% off of each pair. So how about 40% of the first price? 40% of 50 is equal to, I don't know, we'll figure it out. And we get 40% off each pair. So we get 40% off the $50 for that pair of shoes, and we get 40% off of the $32 pair of shoes. Now you might think I misspelled this, but really if you get 40% off, we got to find what 40%, or we got to find 40% of 50. 40% off means you want to find 40% of 50, so let's do that. 40% of 50, use your calculator. That's 20 bucks. 40% of 32 is $12.80. Now, that is not how much you're going to pay for these shoes. Be careful. That is the discount that you get off each pair of shoes. 40% off means if you find 40% of 50, which is $20, you're actually going to pay $50 minus the 40% off, which is 20. You're going to pay 30 bucks for the $50 pair of shoes. 40% off of 32 means you're going to take the $32 that you originally were going to pay. 40% of that is $12.80. That's the discount that we get. So $32 minus $12.80, that is $19.20. Two totally different discounts going on here. How do we find out how much we pay on this second offer? You pay 30 bucks for the $50 pair of shoes. You pay $19 for the, or excuse me, $19.20 for the $32 pair of shoes. If you add those together, $30 plus $19.20 is $49.20. Which one looks like the better deal to you? Bam, the one I put the box around. The second offer is the better buy. And that's all you got to write for a sentence. As long as you show your work, some type of work like this. We didn't do any ratios, proportions, rates, or anything like that. This one here was just kind of eyeballing it. You know, the first offer again, and I highlighted that in the wrong color. I see that now. This is actually the second offer over here in green. But again, showing your work here, you pay 50 bucks for the first pair. But this offer, the first offer says you buy one pair at 50 bucks, you get the second pair half off. That's where that 16 came from, because that's half of 32. Be careful with this one. A lot of folks will say, they'll find 40% of 50 and they'll say, hey, we're paying $20 for the pair of shoes. That is not right. You get 40% off. So 40% of 50 is 20 bucks. That's how much money you're going to be discounted. That's how much money you're going to save. So you're still going to pay 30 bucks, because $50 minus that 40% discount is $30. And the same thing applies to that $32 pair of shoes. But we're still paying much, much less. I mean, heck, we're getting 2 pairs of shoes for less than the price of one with that second offer we have there. So that's it for that one. On to number 13. Mary and Steve stood side by side one sunny day and noticed that their shadows were different lengths. Mary measured Steve's shadow and determined it was 10.2 feet. Steve measured Mary's shadow and determined it was 8.9 feet. If Steve is 6 feet tall, how tall is Mary? What we're doing here, and I'm not going to get too elaborate on this, but we got similar triangles. We got some... I'm guessing Steve is probably the taller guy, and the reason why we can say that is because Steve's shadow was 10.2 feet. Mary's shadow was shorter. I know my triangles look isosceles, if you remember that term, but nonetheless, we don't really need, you don't have to draw these triangles if you don't want to. What we can say, we know that Steve is 6 feet tall. So 6 feet tall. But what about Steve's shadow? He's 6 foot tall, and Steve's shadow is 10.2 feet shadow. Now, what do we know about Mary? All we know is that Mary's shadow was 8.9 feet. So Mary had an 8.9 feet shadow. And the question we're trying to answer is, how tall is Mary? Well, we know that Steve is 6 feet tall. Well, that's his height. We want to find Mary's height, so we're going to put that on top. Mary's height is X feet tall. Let's cross multiply to solve this. 6 times 8.9, cross multiplying. 6 times 8.9, we get 53.4. Set this equal to the other cross product. 10.2 times x is 10.2x. Divide both sides by 10.2. We're trying to get x by itself. They cancel out. So 53.4 divided by 10.2. Let's round to the nearest, oh, what does it say, 10th. So how about 5.2 is equal to x? Make sure you're checking on your calculator. You should get 5.2. So therefore we can say the question we're trying to answer is, how tall is Mary? Mary is 5.2 feet tall. Now, you could use, that's an approximation. You could say Mary is approximately 5.2 feet tall, since we did round to the nearest 10th. All right, what else do we got? 14, how many more problems we got? 14, 14 and 15, so we're getting there. Number 14. A bottle contains 165 tablets. If each tablet contains 200 milligrams of medicine, how many grams of medicine are in the bottle? Two ways to approach this problem. There's 165 tablets in a bottle. Each one of those 165 tablets has 200 milligrams of medicine. The first way you could approach it is this. Well, if we take 165, that's how many tablets we have. If we multiply it by 200, now be careful though, that is 200 milligrams. There's 200 milligrams for every tablet. If we multiply it by 165 tablets, 165 times 200, we get a big answer of 33,000, but this is milligrams because we were given milligrams here. If there's 200 milligrams per tablet and there's 165 tablets, therefore if you multiply these, you have a total of 33,000 milligrams in all. But notice the question says, how many grams? What can we go back to here? We're talking about metric system. King, Henry, drinks, Ucky, dark, chocolate, milk. And what we're trying to do here is we're trying to convert from what to what. We have milligrams given. So we're way over here on the right. But the question says how many grams. So we want to convert to the unit. Remember the notes in class, the unit represents grams. It could represent liters or meters. In this case, it represents grams. So converting from milligrams to grams, you move 1, 2, 3 places to the left. So we go up here to our decimal here. Where is our decimal? It's right there. Let's move it the same number of places. 1, 2, 3 places to the left. 1, 2, 3. Therefore, we can say 33,000 milligrams is the same thing as 33 grams. This is a real world problem, so therefore we need to say there are 33 grams of medicine in the bottle. That's number 14. Last but not least, if you made it this far, bravo. You're mixing some concrete for a home project and you've calculated according to the directions that you need at least 15 liters of water for your mix. If you've ever tried to mix concrete, you get concrete in this sandy, rocky mixture from like Lowe's or Home Depot. You got to mix water with it so it settles and then it becomes concrete. So you can walk on it or put some posts in the ground and hold those posts in the ground. Most people put posts in the ground and fill them in with concrete, but you got to have some water to let that concrete settle. You have a 1 gallon container to measure your water. How many times will you need to fill the container? Round to the nearest whole number. Well, what we were trying to figure out is we need 15 liters of water. That's what the bag says. The bag is in metric units. But what we want to do is we want to convert 15 liters to some number of gallons. All right. Now, let's do that first. Now, you see a 1 gallon container. If we can figure out how many gallons 15 liters is, we'll know how many times we have to fill this 1 gallon container up. Well, how do we do that? We need to back up a little bit. Let's back up to an earlier problem. Let's see here. How about there? Oh, I got lucky. Capacity. Since we're going back and forth between the metric and the US, Let me copy this table over. The reason why I'm copying this table over is because liters is in metric and gallons, that's in US measurement. That's exactly what we have here. Now, we're in a predicament. I talked about it earlier in the video. Which one of these do we want to use? Because we get two totally different answers, or at least we did earlier in the homework. I'm going to use the first one. Let's see. We'll use both of them since we're getting close to the end of the video. But if we get two different answers, I'll pause the video, I'll pull in some Google stuff, and we'll see what happens. But we're trying to convert from liters to gallons because we have a 1 gallon container. We got to know how many times we fill this 1 gallon container to get 15 liters. Let's use this first one here. 1 liter is the same thing as 0.26 gallons. Now we're trying to figure out how many gallons, X gallons. I know I wrote 2 L's up there. I'm not the best with my abbreviations, but we got 15 liters. 1 liter is the same thing as 0.26 gallons. Well, how much is 15 liters? How many gallons of water will that be? Let's cross multiply. 1 times X is X. This is equal to the other cross product, 0.26 times 15. We get 3.9. So right now I'm saying 3.9 gallons of gas. Let's see how it might not be different. It depends on the rounding. The rounding can make a big difference. Sometimes it doesn't. It just depends on the problem. So let's set up another proportion based on this second one here. How about 3.79 liters is the same thing as 1 gallon of gas? Let's set this equal to. We're still trying to solve the same proportion. So over here we have 15 liters over X gallons of gas. Notice I still have the liters at the top and the gallons at the bottom. If we cross multiply, we have 3.79 times X is 3.79X. Cross multiplying the other way, 1 times 15, that is equal to 15. Dividing both sides by 3.79 to get X by itself. I don't even like this one as much as I like this one because we already had X by itself when we multiplied, but hey, we got X by itself now. Take 15 and divide it by 3.79. We get an answer of X is equal to. Now, depending on where you round, grab your calculator. If I round to the nearest, let's see here. Let's round to the nearest thousandth. How about 3.958? 3.958. This answer we got from the first one, and this answer we got here was from this one. They're pretty close. And the reason why they're different, if you watch the earlier part of the video, I got on a crazy, probably 10-minute tangent talking about how rounding can affect your answers. These measurements are approximate. That's so important. That little squiggly line, so they're not perfectly equal. That is an approximation. That decimal there, this number here is rounded. This number here is rounded. That's why your answers will be different. It wouldn't hurt my feelings if you said this. It's approximately, okay, let's do this. Let's say 15 liters is approximately 4 gallons. And you might say, well, where does 4 gallons come from? I'm just rounding to the nearest whole number. Oh, well, look, lucky us. It says right here, round to the nearest whole number. So we got lucky there. 15 liters is approximately 4 gallons. Therefore, we would need to fill the 1 gallon container 4 times, because if it's a 1 gallon container, you want to get 4 gallons of gas, or not gas, but 4 gallons of water. You're going to have to fill it 4 times to mix with the concrete. I think it might have said cement. No, it said concrete, so we're good. But yeah, that's it for that one. And finally, I think we are done. Did we cover all the questions? Yes, we did. So again, here, this last problem, that the approximation thing, those little squiggly lines, that means approximate. That rounding thing is crucial, and you'll see that later on in other math classes. But if you can do all this stuff, you're good. Or if you can do some of it, you'll be fine. Notice I didn't show a lot of work in regards to doing a lot of multiplication or a lot of division on pencil and paper techniques. I do want to see your ratios. I do want to see your proportions or your rates and things like that. But that is it for this video. Very long. I hope it helped.